In the last lecture, we had talked about the basic quantum postulates and had essentially brought in what are the quantum postulates necessary for being used in quantum computation. The basic idea was that a quantum state is represented as a ray in an abstract linear vector space known as the Hilbert space. And what we said is that it is not a particular vector which represents a physical state, but a ray, meaning thereby that there is no difference physically between a particular vector and a vector which is a constant multiple of the same vector. So this one-dimensional subspace of the Hilbert space essentially represents any physical state. Having done that, we talked a little bit about the type of operators which would be there in such a Hilbert space. The job of the operator would be to act on one such vector and take it to another vector in the same Hilbert space. And we had seen that the algebra with which we are concerned with are linear algebra. Now what we want to do today, since we are interested in computation, we are going to be talking about what is the smallest unit of information that one can talk about while dealing with quantum mechanical regime. For instance, in classical computation, you are aware that we talk about bits which take the value 0 or 1. And these bits, which in order to distinguish from their quantum counterpart, I will be using the word C bit for it. C bit meaning a classical bit. And the corresponding quantum bit, we will be calling it a qubit. So if you recall, my classical bits can take values 0 and 1. And all the classical computation is essentially based on the manipulation that you can do using these bits or a collection of bits. Now the corresponding quantity in quantum computation is known as a qubit, and there is a very big difference between them. So what I will say is this, that I am working now in the smallest space that is possible. This is two-dimensional Hilbert space, in which I will represent the states by a 0 or a 1. Okay. Since these are quantum states, I choose them as an orthogonal basis in that state, such that my 0, 0 scalar product is equal to 1, and 0, 1 equal to 1, 0 is equal to 0, and of course 1, 1 is also equal to 1. This is the properly normalized bits. But there is a very big difference between them. The difference is that while a classical bit or a C bit can take the value either 0 or 1 at a time, in quantum mechanics, the smallest bit of information can be a linear combination of 0 and 1. For instance, in this context, I will say some statements like this: 0.2 times 0 plus, let us say, 0.5 I is the square root of minus 1 times 1. This makes perfect sense. So any linear combination of the basic qubits, namely 0 and 1, with complex coefficients, that makes perfect sense. Now, I told you last time that since we are talking about a vector in the Hilbert space, in general, when we talk about an Hilbert space of n dimensions, I can represent it by a collection of n complex numbers, and meaning thereby I can represent a state equivalently by means of a column vector. In this case also, I also talk about the matrix representation. For example, the state 0, we can use the matrix representation 0, 1. You notice it's already normalized, and similarly a state 1 is given by the matrix representation 0, 1. So therefore, when I say that I talk about a linear combination of this 0 and 1, for instance, we talk about a times 0 plus b times 1, where a and b in general are complex. Its matrix representation will be a, b. So a, b complex. Now, what is the difference between this and the corresponding classical thing, other than the fact that I am talking about that a quantum state can be simultaneously in a linear combination of the basic states which are 0 and 1. The point is that when you talk about a linear combination, the amount of information that it has is of course lot more than there would be if it was either just the state 0 or the state 1. But nevertheless, this information is hidden. The information is there in the qubit, but you are unable to get it. Now, in order that we can extract information from such a qubit, we will have to make a measurement. Now, when I make a measurement, you remember last time I told you that there is a Copenhagen interpretation of the state, the quantum state, and the Copenhagen interpretation says there is a probability of its occurrence. Now, what happens is this, that if you are trying to measure such a state in what I am at this moment calling it computational basis, illustrate it a little more as I go along. The computational basis simply means your measuring equipment is also using the state 0 and state 1 as the basis for measuring the states. So this is what is known as a computational basis. So if you have a state like this and you are making a measurement in the computational basis, then you are not going to get a linear combination as a result. You are going to get the state 0 or the state 1, which is what I called as the collapse of the wave function postulate of the Copenhagen interpretation, and you will get state 0 with a probability given by a by square root of a square plus b square. And this is the probability amplitude of the state being measured as 0. The square of that, of course, is the probability. And likewise, the state 1 has a probability amplitude of being measured as b by square root of a square plus b square. So probabilities are just squares of this number, namely a star divided by a mod a square plus mod b square. So therefore, the representation is measured, the quantum state is measured with a probability. So measurement yields either 0 or 1 with a probability. So let us now see what is this qubit. How do you get it physically? I have said already that a qubit is the smallest unit of quantum information, just as the smallest bits of classical information were 0 and 1. Now remember that even when we made the statement that the smallest unit of classical bit is 0 and 1, we always know that there is a method of getting this 0 or 1. For instance, one of the ways in which one gets the state 0 or the state 1 is to use two electrical levels which are separated by, let us say, 5 volts or so. So the ground state, that is the 0 voltage state, could be taken as 0 and a 5 volt state could be taken as 1. This numbers may differ, but that is roughly the idea. Now the point is this: what do I mean by a qubit? What type of physical system it represents? Now there are many ways of looking at it, but basically what it means is that if you have any bistable system, meaning thereby a quantum system which can exist in one of the two states at a time. So for instance, the most common way of understanding it is to realize that to talk about a spin of, it could be spin of an electron, it could be anything with spin half, for instance. For example, it could be spin of a proton, a neutron, and I don't have to necessarily restrict myself to the elementary particles like this. I could even be talking about a silver atom's spin and things like that. Now, when such a system, an electron, proton, neutron, or a silver atom, or whatever you have, is put in a magnetic field, which we will take it as arbitrarily z direction, then there are two values of the spin that comes with it. The z component of the spin can be either a plus half, so this is what is written as sz equal to either a plus half or a minus half. So this could stand for one of the states, let's say 0, and this could stand for the other states, let's say 1. And the equipment with which you control this is what is known as the Stern-Gerlach apparatus. But a much easier way of understanding or realizing this is to talk about the polarization state of a photon. As you know, photon is essentially the particle nature of light. So if I have a single photon, which let us say is propagating along the z direction. Now such a photon has its direction of polarization either along the x direction, basically the direction of polarization is in the xy plane, which is perpendicular to the direction of the propagation. So therefore, since, as you know, that the electric field and the magnetic field associated with such a photon will be mutually perpendicular, if I am talking about a photon which is polarized, so I can take the electric field associated with it along one of the directions, let's say the x direction, and so therefore again I am talking now about two mutually perpendicular directions perpendicular to the direction of propagation. So if the direction of propagation is the z direction, then I can take x direction as one of the directions of polarization, which I will call as the horizontal direction, and the other perpendicular direction, namely the y direction, I can take as the vertical polarization. These are just nomenclatures. Now this is just illustrative. This is just illustrative because what one could do is, instead of taking along the x and the y direction, I could also take, for instance, if the photon is propagating along the z direction, I can take, all right, so this is my z direction of propagation, and I can take one of the directions as making an angle of 45 degrees with the z direction, the other one making 135 degrees with the z direction. So this is This is not in the same plane. Ideally, I should put them in a slightly different notation. So this type of a basis will be called as a diagonal basis. So in a diagonal basis, one of the directions is taken as making 45 degrees with, let us say, x-axis, or 45 degrees with computational basis. And the other one is at 135 degrees with the same direction. So this is a pair. Now if I represent the state which is making 45 degrees angle with the horizontal direction, I can write that state as a plus, which is a notation I use, and normalize it 1 over square root of 2. Okay. This is pictorial. I could write it as 0 plus 1, but let me write it pictorially as horizontal plus vertical, which is just another way of writing 1 over square root of 2, 0 plus 1, and the minus state, which is 1 over square root of 2 minus 1. This is not a very convenient notation to use in writing, so therefore we will be using that plus is equal to 1 over square root of 2 of 0 plus 1 and minus is 1 over square root of 2, 0 minus 1. So these are two possibilities. We could also consider a situation where I take an atomic system when the electron is in the ground state of the atoms, that's one of the state, and when the electron goes to the excited state, that's another state. So for instance, just to make it clear, supposing you take hydrogen atom. I know that in the ground state, when the electron is in the ground state, the energy is minus 13.6 electron volt. Now if the electron is excited to the next excited state, n is equal to 2 states, then I know that the energy is minus 13.6 divided by 4 electron volts. Now you notice there is a substantial difference between the two states. So therefore I could use when the electron is in the ground state as one of the states, stable state. When it's in the excited state, it's another state. So are the spin half system or bistable system, are they the only possibilities? Though we will be talking only about such situations, in principle for quantum information processing, it is possible to think of a situation where we talk not about two states, but about, let's say, 3 states, a state of triplet, the triplets of an atom, atomic state. Such states, instead of being talked about as a qubit, will be talked about as a qubit. Other than talking about these names, I will rarely have anything to do with this. So this is basically 3-state system. And in general, if you are talking about a d-dimensional system, the corresponding unit of information is called a qubit. But these are just nomenclatures and we will have very little to do with it. So I will continue with my discussion of the qubit. So basically I am talking about a situation where I have a bistable state. As I said, a physical state will be associated with a ray, which is the direction in space. Now, There is a beautiful picturization that works. If you associate with the ray with a space direction, I have written that direction as r, which is the x, y, z component in space, and the direction is such that the rth component of the spin is equal to half. So let us look at the algebra associated with such a thing. Now we are aware that for spin half, the qubit representation is given by vector s is equal to sxi plus syj plus szk. This is an important point which is used frequently, so I would spend a bit of a time on it. The sx is the x component of the spin, and as we know that the spin projections along any direction has a value either plus h cross by 2 or minus h cross by 2. Now if you look at the spin operators, then the x component of the spin operators is represented as h cross by 2, a matrix 0, 1, 1, 0. So let me come back on the, so Sx is h cross by 2, 0, 1, 1, 0. Now remember, I am still in the two-dimensional Hilbert space, so that my operators are 2 by 2, because they have to act on states like alpha, beta or AB and giving me a state of this type. So therefore, the operators which act on such a state, they are of this structure. Now, Sy is equal to h cross by 2, 0 minus I0. Sz is h cross by 2, 1, 0, 0 minus 1. Now you would wonder, why am I writing like this? Now these matrices, which are written as sigma x, h cross by 2, sigma y, and this is h cross by 2, sigma z. These are known as Pauli matrices. The Pauli matrices have a very important role to play in deciding how spin vectors, the states transform, and so therefore we would be dealing with it quite a bit. Another thing is that it can be shown that along with identity matrix, now identity matrix is obviously 1, 0, 0, 1. If you take this collection of Pauli matrices, any 2 by 2 matrix can be represented as a linear combination of these 4 matrices. These Pauli matrices, they do not commute among themselves. We will be talking about that a little later. Now I talked about a beautiful geometrical representation. So I said that what we do is choose a direction along which the rth component, I am choosing a direction r, or if you like unit vector n, along which the component of the spin has a value h cross by 2. Sometimes the h cross is not explicitly mentioned, but it's always understood. Now let's look at a Pauli matrix along an arbitrary direction. So far I have given you the Pauli matrices along the x, y and the z direction. Now what we will do in the next lecture is to talk about a representation of the Pauli matrix, okay, in an arbitrary direction. And so far we have been talking about the spin projection, the vector along the z direction. Now what we will do is this, we will find out what are the eigenvalues and the eigenvectors of a Pauli matrix along an arbitrary direction, and then out of that we will choose that direction in which the eigenvalue of the Pauli matrix happens to be +1. Remember that I said that the spin has a projection plus h cross by 2. So I am removing that h cross by 2 because the spin vectors and the Pauli vectors have a factor h cross by 2. So therefore, I will be interested in that direction in which the Pauli vector has an eigenvalue +1.